This is it, episode 1 of General Relativity. We made it, guys. Okay, you probably came to this series expecting a lot of mathematics, and there will be a lot, but not so in this video. I'll just be presenting the bare minimum of geometric algebra, and mostly discussing the geometry therein contained. First, I'll cover the traditional view, which is what most folk learn initially. Second, I'll cover the sphere view, which is similar to the traditional view. And third, I'll cover the mirror view, which is dual to the sphere view and is also my preferred view of geometry. It's important to understand all three of these views because the geometric interpretation of GR which I will be presenting uses all three of them. Why does it? Well, in reality, these three views are just different ways of looking at the same geometric object. And in some context, one view is more intuitive than another, and it's best to be familiar with all three. Near the end, I'll motivate this more with some examples. But don't be too worried. I'll stick to 2 dimensions for the majority of this video, and only at the very end will I jump into the 4 dimensions needed for GR. And before we really get into stuff, remember to comment any questions, support, or criticism. I check the comments frequently and enjoy community feedback. If you have more complicated questions, then come to my Discord server and bring it back from the dead. The link is in the description. The basis for the 2-dimensional geometric algebra has a unit scalar, 2 unit vectors, and 1 unit bivector. As I said earlier, I won't cover the algebraic properties in depth here. I'll only be discussing the geometry. In the next video, I will introduce geometric algebra more rigorously. In the traditional view, the scalar doesn't really represent anything, but the vectors in the traditional view are simply the familiar pointy sticks of yore. And the bivector is the parallelogram formed by these vectors. So hopefully you can see that in the traditional view, vectors are oriented line segments, bivectors are oriented plane segments, and in general, a k-vector is an oriented k-volume segment. Notice how when the bivector is made, it is quite literally just 2 vectors joined together. So any k-vector is then k-vectors joined together. Let's just briefly recall the basis for 2-dimensional space. In the sphere view, the unit 1 serves as the point of origin for the space. This is shown as a gray dot on screen. Then the basis vectors are spheres which pass through the origin. And for those hearing this for the first time, a sphere is a line with intrinsic orientation. And this implies that the bivector is the xy plane, which is intrinsically oriented. Like the traditional view, the bivector is the join of the 2 vectors. So in general, any k-vector is an intrinsically oriented k-volume, not a volume segment, but the full volume. One last time, let's look at the basis for 2-dimensional space. In the mirror view, the unit 1 represents space itself. So for simplicity, I've just not shown it on the screen since the screen is the unit 1. A mirror is a hyperplane with extrinsic orientation, and a hyperplane is a geometric object whose dimensionality is always 1 less than the space in which it lives. We are in 2-dimensional space right now, so a hyperplane is a line. This line then has an orientation given by the vector in the traditional view. Notice how this traditional view vector is outside the line, and this is why it's called an extrinsic orientation. For those wondering why this is called a mirror, I have a video which explains this more thoroughly. You should check it out. A card should appear sometime around now in the top right of your screen. The bivector is then the intersection of these 2 mirrors and represents the origin with an extrinsic orientation given by the traditional view's bivector. In contrast to the traditional view and the sphere view, in the mirror view, the geometric objects lower their dimension while the algebraic objects raise their dimension. Thus, in general, and within a d-dimensional space, a k-vector is a d minus k volume. Let's talk a bit about why we need to know about all these views. Really, it is not 100% necessary. You could learn all the math for GR with no discussion of the views for geometry. However, you would lose access to a lot of intuition, because GR is all about geometry. The power of knowing the different views manifests when dealing with many different concepts. For example, the stress-energy tensor is really the stress-energy vector in geometric algebra. Here is the sphere given by the stress-energy vector in 2 dimensions, telling us where the stress-energy is going. And here's the mirror, or hyperplane, through which the stress-energy passes. So both geometric objects describe different aspects of a single phenomenon, the stress-energy flux, through a hyperplane. Through this, I hope you can understand how sphere lines and hyperplanes are dual concepts. And this was a good example in my opinion, since the Einstein equation simply says that the curvature vector is equal to the stress-energy vector, meaning the Einstein equation is easily visualizable and understandable. This means that if you can understand this example, you can understand the Einstein equation. Another example is of the connection bivectors, which we will discuss in a later video. The bivectors act simultaneously as the hyperaxis of rotation for infinitesimal Lorentz transformations and as the changing differential areas between 2 coordinates in spacetime. The hyperaxis of rotation comes from the mirror view, and the changing differential areas come from both the traditional and sphere views. To assign geometric views to the basis of the spacetime algebra, we must first know the basis. There's one scalar, there are 4 vectors, one for each orthonormal direction in spacetime, there are 6 bivectors, there are 4 trivectors, and there's one pseudoscalar. Now we can see what the corresponding geometric objects are for each view of geometry. For the traditional view, scalars don't really represent anything other than a value. Vectors are oriented line segments, bivectors are oriented plane segments, trivectors are oriented volume segments, and quadrivectors are tesseract segments. And yes, the more accurate term is 4-volume, not tesseract, but tesseract sounds cooler. For the sphere view, scalars represent the origin, vectors are intrinsically oriented sphere lines, bivectors are intrinsically oriented planes, trivectors are intrinsically oriented volumes, and quadrivectors represent spacetime itself. Lastly, for the mirror view, scalars represent spacetime itself, vectors are extrinsically oriented hyperplanes, bivectors are extrinsically oriented hyperlines, trivectors are extrinsically oriented lines, and quadrivectors represent the origin. Hyperplanes in spacetime are 3-dimensional and so are like volumes, and hyperlines are 2-dimensional and so are like planes. In practice, you can call them whatever you like. For example, in a paper I wrote on Wigner-Little group for photons, I used the mirror view of spacetime and said that vectors are world volumes, that bivectors are world planes, and that trivectors are world lines. I was motivated to call them this because trivectors in spacetime geometrically represent the concept of world lines, and so I just adopted that nomenclature for the remaining basis multivectors. That's it for this video. The next in the series will cover the geometric spacetime algebra.